So we are going to do some more problems and some more tools to study more on the factorization of polynomials over a field before we complete this chapter today. So the first problem we are going to do today is to find whether this polynomial f of x equal to x cube plus 3x square minus 8 is, or that is in q of x. Need to find out whether this is reducible in q of x or not. The theorems which we are going to use here is if f of x is of degree 2 or 3, then f of x is reducible if and only if it has a 0 in f. This belongs to f of x. And the next theorem which you are going to use is if f of x equals x to the power of n plus a n minus 1 x to the power of n minus 1 plus dash 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 a 0, and that is in c of x, has a 0 in q, then it has a 0 m in z, and m divides a0. So these are the two things which you are going to use here. And also another theorem which you are going to see is if f of x belongs to z of x, then f of x is reducible in q of x if and only if it is reducible in z of x. These are the three theorems which you are going to use to find out whether this is reducible or not. See this, first of all, this polynomial is of degree 3, and that falls into this. So it should have, and another thing is f of x here, it belongs to z of x. So f of x is reducible if and only if it has a 0 in z. And this says that this is in this form. The coefficient of the highest power of x is 1, and that is this. So this is exactly like this, and it has a 0 in q, then it has a 0 in m, and m divides a0. That means the 0 of f of x should be a factor of 8, and that implies if f of x has a 0 in c, it should be plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. If none of these are zeros, then we don't have a 0 in z, and that means it is not reducible in Z. So, but if you find the values, I'm going to find only for f of 1, and that's going to be 1 plus 3 minus 8, and which is not equal to 0. So, if you compute for every values, you'll see that f plus or minus 1 not equal to 0, f of plus or minus 2 is not equal to 0, f of plus or minus 4 is also not equal to 0, f of plus or minus 8 is also not equal to 0. And that implies f of x is not reducible in z of x, and that implies f of x is not reducible in q of x. Now we are going to discuss a very important tool to find out whether a polynomial is reducible or not. It's called Eisenstein's criterion. This is going to be used in several places on your studies on field theory. So the criteria is like this. Let P belongs to C. That means P is an integer, be a prime number. Then let f of x is equal to a n x to the power of n plus n minus 1 x to the power of n minus 1 plus dash 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 a 0 that belongs to C of x and a n is not equal to, is not congruent to 0 mod p. A I is congruent to 0 mod p for all I less than n, and A0 is congruent to, not congruent to 0 mod p square. Then f of x is irreducible in z of x. It's a very powerful tool to find out whether a polynomial with integer coefficient is irreducible or not. So the proof actually goes by contradiction. So let us assume that if everything is true, then we'll assume that f of x is reducible, then we'll arrive at a contradiction. That is how we are going to show this proof. So let f of x, and that is equal to a n x to the power of n plus a n minus 1 x to the power of n minus 1 plus dash 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 a0 equals b m x to the power of m plus dash dash b0 times cs x to the power of s plus dash 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 c0 be the factorization of this. Okay, if this is reducible, we can factorize where both m and, sorry, let us take it as r. Let us take it as r and s. Where r and s is strictly less than n. Now, an or n is different from 0 mod p means, what is an? You'll get an only by br times cs. That means br times cs is not equal to 0 mod p. That means this is not a multiple of p, and that implies br is not equal to 0 mod p, and cs is also not equal to 0 mod p, because p is a prime number. Now the next one is ai is equal to 0, or a0 is different from 0 mod p, and p square, and a0 is equal to 0 mod p. See, for all I less than n, ai is equal to 0 mod p, but for p square it is not, a0 is not equal to 0. So that means, what is a0? a0 equals b0 times c0. That means c0 b0 c0 is not equal to 0 mod p square, and b0 c0 is equal to 0 mod p. That means one of them is a multiple of p and other one is not. That means either b0 is a multiple of p, and, or we can write it like this, instead of saying multiple, you can say either b0 is equal to 0 mod p and c0 is not equal to 0 mod p, or b0 is not equal to 0 mod p and c0 is equal to 0 mod p. Only one of these conditions will be true. So what we will do is, let c0 mod, c0 is congruent to 0 mod p. Okay, so once you consider this one, this is 0 mod p, but this is not 0 mod p. See, cs is not equal to 0 mod p, but this is 0. So there will be some CS, the lowest CS. So we'll say let m be the lowest integer such that Cm is equal to 0 mod is not equal to 0 mod p. If it is Cm minus 1, then Cm minus 1 is going to be mod 0. Sorry, 0 incongruent to 0 mod p. Only up to this it is not equal to 0. After that it is zeros. Now we'll when you multiply this, what would be the coefficient of Am? Am is equal to B0 Cm plus B1 Cm minus 1 plus dash 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 dash. This is the lowest integer. So what happens? All these are all zeros. Mod p, because this is the lowest am such that Cm is not different from 0. So Am is equal to B0 Cm, right? And what is B0? B0 is different from B0 is different. See, this is the condition we took. This is the condition we took. So B0 is different from 0. Cm is also different from 0. And that means this is actually is not congruent to 0 mod p. So in this polynomial, except an, all are congruent to mod p. Ai is congruent to 0 mod p. The only coefficient of the power of x that is different from 0 mod p is the first one, the an. So this implies am is equal to an, and that implies m is equal to n. And what does that mean? M is equal to n means, that means n is equal to s. Because see, an is equal to br times cs. So this br, see this m is equal to n means an is equal to b0 times cn. So this cn is actually, this is our r and this is our s. So n is equal to s. And that means that is actually contradicting the fact that s is less than n. So this contradicts the assumption that s is strictly less than n, and that implies f of x is irreducible in CF. Now we will do an important corollary of Eisenstein criteria, and that is let P be a prime number. Then the polynomial phi p of x is equal to x to the power of p minus 1 by x minus 1 is equal to x to the power of p minus 1 plus x to the power of p minus 2 plus dash dash plus 1 is irreducible over z. And this polynomial is called the cyclotomic polynomial. Called the cyclotomic polynomial. The way we are going to show is like this. Define an evaluation map, evaluation homomorphism. Then show that the image of phi p of x under the homomorphism is irreducible. In irreducible over z using Eisenstein criterion. Okay, so if the image is not reducible, if image is irreducible under the homomorphism, this also will be irreducible, and that implies phi of p of x is irreducible, and that is a plan. Now, how do you define an evaluation map? You normally define an evaluation map is like this. Let's say f is a subfield of E, and we are going to define the evaluation map, let's say alpha from f of x to E by phi alpha of f of x is equal to f of alpha. And that is how we defined the evaluation map. So here the evaluation map goes like this. Define the evaluation map, relation homomorphism as phi. This phi is different from this phi. This is a capital phi, okay? Capital phi, and there should be a element here, that is alpha of, and this is actually going to be from q of x. So here this is our f to q of x. This is the extension of q, or q is a subfield of q of x. So this qx is, though it is a map from q of x to q of x, this is actually the extension of q. Okay, and the way we are going to define is, so once you have this one, the meaning of evaluation map is phi of x plus 1 of f of x is going to be f of x plus 1. Or in here we are going to write this as phi of p of x is equal to phi of p of x plus 1. And what we are going to do is we are going to show here that this is irreducible using Eisenstein's condition criterion. And that means this also is irreducible. So this is actually equal to, replace that, x plus 1 whole to the power of p minus 1 by x plus 1 minus 1. And that is equal to, if you expand this one, x to the power of p plus p x to the power of p minus 1 plus dash 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 plus 1 minus 1 divided by x. And that is equal to x to the power of p minus 1 plus p x to the power of p minus 2 plus dash dash dash. The last term will be again p. See, now we are going to apply Eisenstein's condition with the prime number as p. So here A0 an is equal to 1 and ai's are multiples of p. All a's are multiples of p if you expand using binomial theorem. And a0 is equal to p, and that means a0 is different from 0 mod p square. And here, since an is equal to 1, that means an is different from 0 mod p. And ai is equal to 0 mod p for all I less than n. So all these conditions are satisfied for this. And that implies phi x plus 1 of phi of px is irreducible. Using Eisenstein criterion. And that implies phi p of x is irreducible. Over. So. Let us do another result, a very simple one. Let f of x is in f of x and f of x is irreducible over f. If f of x divides r of x times s of x, then f of x divides either r of x or s of x or both. It is something like this. See, if you take a prime number, let us say 3, 3 divides 9 times 5. Right? So that means either 3 divides 9 or 3 divides 5. Here 3 divides 9. Or if this is 9 times 15, so it divides both. And that's exactly what this theorem means. Either this or no. Its proof is very simple. We have another proof coming up in prime ideals, but we'll do it without using any ideals. So what we are going to do is, let f of x does not divide r of x. If it does not divide r of x, then we need to prove that it divides s of x. So we can write s of x equal to f of x times q of x plus g of x using the division algorithm. So what does that mean? That means that r of x times s of x is equal to r of x times f of x times q of x plus g of x. And so this is actually equal to r of x times f of x times q of x plus g of x times r of x. Okay? So we'll take this one here. See, r of x times s of x minus r of x times f of x times q of x equal to g of x times r of x. But f of x divides r of x times s of x, and that is what the assumption is in the theorem. Implies the whole thing f divides the whole polynomial. So f of x divides r of x times s of x minus r of x times f of x times q of x, because this is a multiple of f of x and this is a multiple of f of x. So the whole thing is a multiple of f of x, or it is 0. And that implies f of x, that implies g of x times r of x divides, f of x divides g of x times s of x. But we have already assumed that f of x does not divide this. So it has to divide. So that means if this divides this one, so this, and g of x, the degree of g of x is less than the degree of f of x. And the degree of g of x is strictly less than degree of f of x, and that implies g of x equal to 0. If g of x equal to 0, that implies s of x is equal to f of x times q of x, and that implies f of x divides s of x. So if f of x does not divide r of x, it definitely divides s of x, and that completes the proof. There is a very simple extension to this theorem, make it as a corollary. Let f of x in f of x be an irreducible polynomial over f, and f of x divides r1 of x times r2 of x times dash dash rn of x, then f of x divides ri of x for at least one I. This is just an extension of the earlier theorem. Not going to show this because this is you can do it using mathematical induction, and it is a very straightforward proof. So next theorem is every polynomial f of x in f of x can be expressed as a product of irreducible polynomials in f of x, and this product is unique up to the order and possibly non-zero constants. Meaning f of x can be written as r1 of x dash dash rn of x, where all of them are irreducible, and if you can write it as, let us say, q1 of x dash dash qs of x or qm of x, then n is equal to m, number of irreducible polynomials are same, and you can find ri in some of this as a multiple of q of I, or other way, meaning some ri's could be some uj qj of x. This is not a polynomial in x, but it is a constant in f. So that is what this means. Possibly it's non-zero constants. For example, if you take x square minus 1, you can write it as x plus 1 times x minus 1. But this also you can write it as 2x plus 2 half of x minus half x minus half. So this is our R1, this is R2, this is Q1, this is Q2. Actually this is a multiple of R1. So Q1 is equal to R2 and Q2 is equal to half R2. That's what I meant. So the proof is very simple. So let f of x be irreducible, be a reducible polynomial. Because otherwise we are done. There is nothing to prove. Then that implies f of x is equal to q of x times, or we'll say let's say g of x times h of x. If both g of x and h of x are irreducible, we are done with the first part of the theorem, meaning except the uniqueness, because both of them are irreducible polynomials and we express f of x as a product of irreducible polynomials. If not, continue the process on the reducible polynomials until we get f of x is equal to r1 of x times dash dash rn of x. This has to terminate. So our first part is done because these are all irreducible polynomials. Now for the uniqueness, let f of x is equal to r1 of x dash dash rn of x, and that is equal to, let us say, q1 of x dash dash qm of x. So this implies r1 of x divides q1 of x times q2 of x dash 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 qm of x. R1 of x is irreducible and this divides this. That implies R1 of x is equal to, or R1 of x divides, divides qi of x for some I. For some I 1 less than or equal to I less than or equal to m. So what we do is, if we divide somewhere here, let's say qi, we make I as 1. We are reordering it. So assume that I is equal to 1, which implies R1 of ix is equal to u1 times q1 of x. This has to be a unit because both r1 of x and q1 of x are irreducible polynomials. So the only thing is that it could be a multiple of a non-zero element from F. Right? So if you continue this process, what we'll have is before that, what we'll do is we'll replace here. So that means u1 of q1 of x times r2 of x dash 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 rn of x is equal to q1 of x dash dash qm of x. Here you cancel out q1 from both sides. So that will be u1 r2 of x dash dash rn x is equal to q1 is gone, q2 of x dash dash qm of x. We'll continue this process until we get u1 times u2 times that as un. We are assuming that n is less than or equal to m. Otherwise, we will reverse the process. So is equal to q n plus 1 of x that as q m of x. This is a constant and this is a polynomial. So this implies that m is equal to n and Ri is equal to ui times qi of x, and that is what we want to prove. Let us do a very simple problem using Eisenstein criterion. X square plus 8x minus 2 in q of x. Want to show that this is irreducible using Eisenstein's criteria. So p is equal to 2. Here a(n) is equal to 1, which is not equal to 0 mod p. Mod p is mod 2. And this is n is equal to 2 here. So a1 is equal to 8 and a0 is equal to minus 2. So these are all ai is equal to 0 mod 2. a0 is equal to minus 2 and that is different from 0 mod p square, and that implies x square plus 8x minus 2 is irreducible in C of x, and that implies it is irreducible in Q of x. So we'll do one more problem before we complete this chapter on factorization of polynomials. So this is a very simple problem. We are going to use a result from an elementary number theory. The problem is this: for any prime p x to the power of p plus a is reducible in z p of x, meaning this p is always, a is always less than p. If this is a polynomial in here, a should be less than p. So we are going to do in 2 steps. Before that, we are going to use a simple result, powerful result from elementary number theory, Fermat's theorem. For any prime p, a to the power of p is congruent to a mod p for an integer a in C. So here we are going to do it in 2 steps. Case 1, p is equal to 2. That is the only odd prime number. So if p is equal to 2, we need to show that x square plus 1 is reducible. So there is another polynomial that is just x square and x square plus 1, because a should be either 0 or 1. If it is 0, it is x square which is reducible definitely. X square plus 1 is equal to x plus 1 whole square, because if you expand this one, this is x square plus 2x plus 1 and this is 0 in z2 of x. So this is reducible. So case 2, p is odd. This is only even prime number. Now we use that. So a to the power of p, or we can write it like this, f of x is equal to x to the power of p plus a. So f of a to the power of p plus a, and that is equal to minus a plus a. Because of that, this is odd. Okay, so a to the power of p is equal to minus a. So minus a to the power of p, and p is odd, and that is a, and that is equal to 0. And that implies a is a 0 of f of x, implies x minus a is a factor of f of x, and that implies f of x is reducible.